In this video, we are going to learn about functions of several variables, which extend the work we've done with functions of single variables into higher dimensions. Starting off, a function of two variables, f of xy, maps an ordered pair input xy to an output f of xy. So notice our input is now a point as opposed to a single value, and our output is still a single value, now denoted f of xy. The domain D of a function f of xy is the set of all ordered pairs xy for which the function is defined, and the range is the set of outputs f of xy such that any input xy is in the domain. Another way you can see functions expressed is with a function mapping. So that would be a function f which maps, let's say, 2 space to the reals. So what this is expressing is that our input is in 2 space and our output is a real number, a single value. We could have R3 mapping to the reals, and there our input would be 3 space. We could switch these, which would work for our vector functions, where we had a real number input, a single input, that outputted a 2 space or a 3 space vector in those cases. So just another way to express functions. Consider the phi being equal to x squared plus y squared. So first question, what is the domain of the function? In this case, there are no elements of the function that would create a domain restriction, and those typically are square roots, denominators, right, a rational expression, a natural log function. None of those appear in this function. So the domain is going to be all of 2 space or R2. Evaluate f of 3, 1. So x will be 3, y will be 1. We input that into the function. So 3 squared plus 1 squared. So f of 3, 1 is 9 plus 1, so we get 10. Right? So our input of 3, 1 maps to an output of 10. And in this case, it's not really the math that I'm concerned about. It's more expressing the mechanics of evaluating a function of two variables, how both inputs work together now. So f of -2, -4. So -2 for x, -4 for y. So that's going to be 4 plus 16. So f of -2, -4 is equal to 20. Now the last question, what is the range of the function? Now this is not always an easy question to answer, even with a single variable function. But in this case, our function is just x squared plus y squared. So from knowing what squaring does to a value, the lowest value we'd be able to output in this function is going to be 0. And that would be if x and y were both 0. And then any other input would give us a positive output, because we're squaring the x and we are squaring the y and we're finding the sum of those two values. So the range of the function in interval notation is going to be 0 to infinity. And we'll see this later in the video. I also graphed this function so that we can see what the surface looks like, and that will confirm the range that we've defined here. Now, finding a domain is a question that we were asked quite often with a function of a single variable. We typically did not sketch that domain. Maybe on a number line every once in a while if there was an inequality that we needed to figure out where the values were. But now that our domain is in 2 space, we often sketch it so we can get a visualization of what that domain looks like. All the restrictions follow from single variable functions. So the first function, f of xy, being equal to the square root of 16 minus x squared minus y squared. So the values inside, or the radicand, has to be greater than or equal to 0. So 16 minus x squared minus y squared has to be greater than or equal to 0, which if we move the squared terms over, 16 is greater than or equal to x squared plus y squared. Okay, so that's a circle of radius 4. So 1, 2, 3, 4, 1, 2, 3, 4. I'll put the intersections with the axes on. 1, 2, 3, 4. I go 1, 2. Let's try to draw our best circle. It's a solid circle in this case because we do have equality. If we had strict inequality, we'd have to draw the circle as a dashed line. And then if x squared plus y squared has to be less than or equal to 16, reading the inequality in the opposite direction, that means any point inside the circle. So we shade inside, so there is the domain. All right, so any point on or inside the circle of radius 4 centered at the origin. Next up, we have the function g of xy, which is defined as the natural log of 3 minus x minus y. So for a natural log function, the input has to be greater than 0. So that's a good starting point. So 3 minus x minus y has to be greater than 0. So we can say 3 minus x is greater than y. Okay, so this is going to be a line. So we'll graph y-intercept at 0, 3. Slope of negative 1. So we'll put a few points. We don't have to get too crazy here. Strict inequality means it's going to be a dashed line. So we'll make a dashed line through the points. And then if y is less than 3 minus x, then any point below. If you're ever not sure where to shade, you could always use a test point, right? So we test the origin here. So plug 0 in, is 3 greater than 0? That would be a true statement. So we should shade on the side where the origin is located. All right, so there are the first 2 domain problems. Let's look at a few more. So f of xy equaling to y over xy minus 1. So here we have a rational-like function. The denominator cannot be equal to 0. So xy minus 1 cannot be equal to 0. So that means that xy cannot be equal to 1, which rearranging here, y cannot be equal to 1 over x. So this is the graph of a hyperbola. So 1, 1, and negative 1. So every 2 boxes is 1 here, just to give us a little space to work. So we'll sketch in. So we can't be equal to the hyperbola, so the hyperbola will be a dashed line. Move out of the way. Okay, so there's our dashed in hyperbola. And then the domain is any point that's not on the hyperbola. So I'll grab a different color to shade. So shade in between our dashed, and then above and below. So the domain is all points not on the hyperbola, y equaling to 1 over x. Our last example for domain, g of xy equals e to the xy minus sine of x plus y. So the exponential function doesn't create any domain restriction, nor does the sine function. So then let's look inside of each, because they are compositions. So x times y also doesn't have any domain restriction. There's no square root, there's no natural log, there's no denominator to deal with. And the same thing with the sum of x plus y. So because the composition of both of these don't have any domain restrictions, then the domain here is all of 2 space, or R2. And sketching it is really just shading the whole axes. Right, so I included this example more to talk through the fact that the exponential function and the sine function don't have any domain restrictions. Same with cosine, and if we change the base instead of e, base 2, right, we wouldn't have any domain restrictions there. Okay, so if a function of 2, or if f is a function of 2 variables with domain D, then the graph of f is the set of all points x, y, z in 3 space such that z equals f of xy and xy is in the domain. So essentially the takeaway here is that the function output represents the z coordinate of any point in 3 space. Right, so I'll underline that part there. So in single variable functions, we often interchanged y and f of x. Right, the output of a function we consider the y coordinate, and that's how we graphed all of our 2-dimensional functions. So here, we'll consider z to be the output of the function. X and y are the inputs, and that's how we're going to generate our graphs. Now, unlike 2 dimensions where we're able to graph many of our functions by hand, it's going to be much more difficult to do that in 3 space. You can see I've included 3 graphs just for us to look at, all with some combination of x's and y's and squaring. And we could probably graph these by hand if we really needed to. But once we start to introduce exponential functions, sine, cosine, the graphs are going to get pretty interesting and more challenging to graph by hand. And in those cases, we're going to use a computer or a graphing program so that we can get a good visualization, and also we can manipulate it. We can rotate it, we can zoom in, we can zoom out. So any software that allows us to graph in 3 space is going to be advantageous for looking at some of the graphs of more challenging functions. But here, just to look through 3 of them, f of xy equaling to x squared plus y squared. So this is an elliptic paraboloid. This is the function that we studied on the first slide of the video. So we can see that the range is in fact 0 to infinity, including 0. For the second function that I graphed, we have x minus y quantity squared. So this is a parabolic cylinder. So we see the parabolic part, the cylinder piece. Okay, and in this case, when y equals x, okay, it's going to be 0. So we could see that reflected in the graph as well. So that's an important takeaway. Even if we can't graph these by hand, trying to pick up on traits that are reflected in the surface based on the definition of the function, right? So for here, when y equals x, the output would be 0, and we see that reflected in the function. And then the last one, f of xy equaling to 1 over 1 plus x squared plus y squared. So the maximum output would be 1 based on this function definition. We can see that reflected in the surface, and then the values kind of go out and down. It's never going to be equal to 0, so the surface is going to stay above the xy plane as it continues out along each of the axes. Now, we can't graph by hand very easily, some functions more easily than others, but we can graph something. And that is the level curves. So the level curves of a function of 2 variables are the curves with equations f of xy equaling to k, where k is a constant in the range of f. So we are setting the output equal to some constant. So really this is like saying z equals k. And we're going to graph the curve we get for each constant that we replace z with, or f of xy with. And we're going to represent all of those on the same 2-dimensional axes on the xy plane. And by comparing the level curves, we can get an idea of what the surface looks like, or maybe some properties of the surface that would be helpful to answer further questions. Okay. Similar to traces, the difference, it's a subtle difference, but the difference is a trace, we set the inputs constant. We said x equals 1, x equals 2, x equals 3, or y equals 1, y equals 2, y equals 3 to create our traces in the coordinate planes. Level curves, we're setting the output constant, and we're looking at what the curve looks like in the xy plane only. So our first example, sketch level curves of the function f of xy equaling to 4 minus x minus y over 2. So if we replace the function with z, hopefully we can notice that this would be the equation of a plane. Now we're just representing it as a function. So level curves, let's graph a few of them to get a sense of what they look like. So we'll start with k equals 0. And again, we write k instead of z just to really emphasize the fact that it's some constant that's being put in for the function output or the z value. So we have 0 equals 4 minus x minus y over 2. And if we solve that, so we have x minus 4. Actually, let's erase that. Let's just move the y over. That's going to be easier. So y over 2 equals 4 minus x. Multiply both sides by 2, so y equals 8 minus 2x. So we graph that, and that's going to be our first level curve. So 0, 8, slope of negative 2. I'm going to use the line tool just since we're going to graph a few lines here. X-intercept would be 4. All right, so there's our first level curve. Let me adjust that a little bit. So we want to label that. All right, so this is going to be k equals 0. There will be arrows. Right? We can draw arrows on the end of each of these. Then we pick the next k value, so k equals 1. So 1 equals 4 minus x minus y over 2. Then move the y over 2, move the 1 over, so 3 minus x. So y equals 6 minus 2x. So we move down to on the y-axis, still have the same slope, and we graph the line. Okay, so we have a parallel line here, and that's when k equals 1. And it's important to label them because we are essentially looking at the line in the xy plane, and then this is the z value that this line exists at this cross section of the surface. And then if we go k equals 2, we don't have to write all of the work out. It's going to be y equals 4 minus 2x. Right, so we have another parallel line here. Y-intercept now 2 down on the y-axis at 4, and we graph our line. Okay, there, and that's k equals 2. We can have negative k values. We can continue with positive k values, right? But that's enough for now. And then it says use the level curves to sketch a graph of the function in the first octant. So essentially, what that requires us to do is we're going to take each of these level curves and bring it back up to the z value where that cross section occurred. So to help us out, we do know how to sketch a plane. So the z-intercept is going to be 4. Z-intercept is going to be 4. The x-intercept is also going to be 4. And the y-intercept is going to be 8. So let's sketch that little triangular portion in the first octant. Okay, so in red, so basically here, this cross section, that's k equals 0. Right, so when z equals 0, we cut the surface. It's a line. We see that line reflected in our graph. And then we would go up to 1. Right, so there would be k equals 1. That's the cross section. And then we'd have k equals 2. And then we'd have k equals 3. And k equals 4 would go through the z-intercept. So we can see how these level curves, they're evenly spaced along the surface, just like they were evenly spaced on the xy plane. Okay, so now we have an example where they did the work for us. And actually, one more, forgot that piece at the bottom. Let's not forget that. So a function f of x, y equaling ax plus by plus c is called a linear function. We spend so much time in two-dimensional mathematics talking about lines, linear functions, graphs of lines. It's important to know what the analogous function looks like in 3-space. And that's essentially a function that's defined as the equation of a plane. All the variables are degree 1. That's why it's referred to as a linear function. Okay, back to this example. Below are the level curves of the cone f of xy equaling to square root of x squared plus y squared, drawn in both 2-space and 3-space on the surface of the cone. Okay, so we have circular level curves. They are evenly spaced out. You see they're labeled k equals 0, 1, 2, 3. And then we compare it to the surface of the cone, and there's a point right there. So that's k equals 0, that's the point. And then we have k equals 1, k equals 2, k equals 3. Right, so each of those z values, the cross section is circular, and we see those circular cross sections or level curves reflected on the xy plane. Right, so this is the xy plane. Now, because they're evenly spaced, as we go and stack them back up in 3-space, it's going to create the surface of a cone. In comparison to the example below, still have circular level curves. Notice they are now not evenly spaced. So how is that going to change the surface in 3-space? So what we can do is we can start to bring each level curve back up to the appropriate z value. Okay, so 0. And then if I mark out, so we have 1, 2, 3, 4, 5. This is your z. your y, your x, just to be thorough. Okay, so we're going to take each level curve. So we have 0. Then at 1, we have a circle like that. Then we get to z equals 2. The circle's bigger, but the radius didn't double in size, right? It's not evenly spaced. So we'll make a circle that's just a little bit bigger than the circle that we just drew. And then z equals 3, same thing. It's going to be a bigger circle, but the radius doesn't grow by as much this time. And then the same thing at 4. We draw a bigger circle, but the radius doesn't grow by as much. And at 5, same thing. Now, because we're drawing this by hand, it's not going to be perfect. But if we connect our level curves like this, well, let's do a little better job on that left side. Okay, we should start to see visually that this is the surface of a paraboloid, an elliptic paraboloid. Okay, for me, the important takeaway in comparing these two sets of level curves is the more compact the level curves are, that means the steeper the surface is going to be. Right? So above, the level curves were evenly spaced out. So there was a linear like, right, the surface of the cone. And then here, the curves got more compact as we went out. So the surface started to get steeper and steeper as we moved up along the z-axis, and that's what created the surface of the paraboloid. Okay, 2 more examples of level curves just to practice with. This is new, right? We never had level curves when we were talking about functions of a single variable. So our first one, f of xy equaling to y minus x squared, and they ask us to pick 3 different k values at -2, at 0, and 2. The important part is we don't necessarily always have to use every k value, but whatever k values you pick, make sure they're evenly spaced, because we want that even spacing to try to pick up on any properties reflected in the set of level curves that transfer to the surface or the graph. Okay, so k equals -2. So we have -2 equals y minus x squared. So x squared minus 2 equals y. So that's going to be the graph of a parabola. And we'll just write all 3 out and then we'll graph. So 0 equals y minus x squared. So x squared equals y. And k equals 2. 2 equals y minus x squared. X squared plus 2 equals y. So we have 3 parabolic level curves, and each with a different y-intercept, right? Translation. So I'll start with k equals 0, the first one. So 0, 0, 1, 1. So notice every 2 boxes is 1 here. So 2, 4, 1, 2, 3, 4. And then the same thing on the other side of the y-axis. Okay, so there's our first level curve. So k equals 0. And then we have k equals -2, so down there, and then basically it's a translation, so we'll just shift every point down 2. 1, 2, and then 1, 2. That does make graphing a little bit easier, thinking of it as a translation. Now they're going to get pretty close together up near the top, and because of the curves that they are. That's k equals -2. And then we can shift every point up to get our third level curve, and that's k equals 2. Right, and we can continue this. We can put k equals -4, -6, +4, +6 here. Hey, but essentially, when we go, or if we want to graph this surface, we can use these level curves, bring them back up to the appropriate z value, and then look to connect them to create our surface. Okay, so now would be a good moment to pause the video, try the problem below, and let's see how we do. Okay, so hopefully you gave it a good attempt, and now you see everything's filled in. I used the opportunity to pause the video and just complete this myself as well. So we see the 5 level curve solved algebraically. There is that plus or minus element because we have 1 equals x squared, 2 equals x squared. And that means that we're going to get sets of parallel lines for 1, 2, 3, 4. And you can see that reflected in the graph of the level curves to the right, which I'll move myself out of the way. So k equals 0 is the y-axis, and then for 1 we have a set of parallel lines, and then 2, and then 3, and then 4, and the level curves start to get more compact, so the graph is going to get steeper as k continues to increase, or the z value continues to increase. Right? And if we were to actually sketch this graph, it would be a parabolic cylinder, right? And we can kind of see that reflected in the set of level curves. Okay, so we've done a few level curves. That's definitely a new idea. Now what happens when we add another value to our input? So a function of 3 variables, f of x, y, z, maps an ordered pair input x, y, z to an output f of x, y, z. So now the output would be in 4 dimensions, so graphing is really difficult now, but we can talk about the domain and the analogous part of level curves, we won't get too far ahead of ourselves, in 3 dimensions. So find the domain of the function f of x, y equaling to z over square root of x plus y minus 2z. So we have a square root function in the denominator, so that means that x plus y minus 2z is strictly greater than 0, because square root greater than or equal to 0, the denominator can't be equal to 0. Combining those 2 domain restrictions, strict inequality here. So essentially, that means all points above the plane, right? So if we wanted to write out a verbal description of the domain, it'd be all points above the plane x plus y minus 2z equals 0, right? And that domain is in 3 space now because the output is in 4 space or 4 dimensions. And then the analogous part of level curves are called level surfaces. So the level surfaces of a function f of 3 variables are the curves with equations f of x, y, z equaling to k, where k is a constant in the range of f. Now, if we want to think of variable-wise, we typically use w next, right? So basically it's saying that w is equal to k, the output is equal to some constant. So describe the level surfaces f of x, y, z equaling to z minus x squared plus y squared. So they're not asking us to sketch, but describe them. So let's start k equals 0. Let's see what we get. So that would be 0 equals z minus x squared plus y squared. So if we solve for z, that would be x squared minus y squared equaling to z. And that's going to be a hyperbolic paraboloid. And then if we take k to be equal to 1, so 1 equals z minus x squared plus y squared. So x squared minus y squared plus 1 equals z. Again, a hyperbolic paraboloid. And k equals 2, k equals 3, that's just going to change the constant. Let's look negative. If we try k equals negative 1, does that change anything? Always important to think about that. So negative 1 equals z minus x squared plus y squared. So x squared minus y squared minus 1 equals z. And doesn't change anything. Still going to have a hyperbolic paraboloid. So describing level surfaces, it would be a set of, right? So it's a set of hyperbolic paraboloids. If you weren't tired of writing hyperbolic paraboloid yet, just one more time, and that would be the best description of the level surfaces. Now, how they translate into 4 dimensions, that's a little bit challenging for us because we don't have a geometric context of what 4 dimensions look like. So we talked about domain, range, we looked at a few graphs and spoke about how using a graphing tool software would definitely be better as functions get more complex. Level curves, level surfaces, and that completes our discussion on functions of multiple variables. Again, with the new elements, it's important that you practice to get comfortable with all of these new ideas.